Thank you, Dean.
Yeah.
Okay, so within the context of the title of this discussion, the Securing the Future of Thin Film Solar Industry, obviously I'm going to talk about this from Oerlikon's perspective. That's obviously where we have the most detailed knowledge, but I think a lot of what I'm going to say is generic. So with that, let me move on. It's a disclaimer. I don't think we need to go through that in detail. So what is the key driver? I mean, Dean mentioned a couple of key points there. I think the most critical one that we see right now is the development of the manufacturing cost per watt peak. So really, with crystalline having compressed its manufacturing cost significantly over the last 12 to 18 months, that's obviously laid the gauntlet squarely at the door of thin film. We now need to demonstrate that we can execute on our roadmaps to bring those manufacturing cost per watt peak down in equivalent step functions to maintain our competitive advantage there. So execution on the roadmap is critical. This applies for all players in the industry, particularly for thin film players right now. One of the points I wanted to highlight here and show you is from Oerlikon's perspective. This chart is a high-level overview of our cost roadmap. It shows you where we were in 2008, where we were able to contract lines which, when fully ramped into production, would have had a manufacturing cost of around about $1.50 per watt peak. In 2009, we were able to reduce this to $1.30 per watt peak. We now can contract today around $1 per watt peak once that factory is fully ramped. And by the end of this year, we will enable technology that, when fully ramped, is able of achieving 70 cents per watt peak. This level of execution is clearly very competitive against the crystalline manufacturers, and this is what we need to achieve. I think what should give us all confidence about the achievability of this type of roadmap is the track record to date. So in the last 2 to 3 years, we have significantly reduced these costs. We've done this through increasing the productivity of a given factory. If you look at this from where we were in 2008 to where we are today, we've actually increased the productivity of one of these units by 100%. That obviously has a significant impact on the capital cost per watt peak and the bottom line manufacturing cost per watt peak. We've reduced the material cost by more than 50%, so as we see here, 53% approximately. And that's very, very important. We always focus very much on the efficiency and that impact that has on the bottom line manufacturing cost. But if you remember, we're talking about some very expensive components that go into these modules. So glass, lamination foils, junction boxes. This is an area where there's a huge amount of potential to reduce cost. And this has been very significantly achieved already to date, enabling a total manufacturing cost reduction of more than 50% in the last 3 years. How are we doing this? This is Oerlikon specifically our philosophy, but I think you'll see similar from other thin film manufacturers. Clearly, technology innovations are driving these cost down programs, and this is what we have to execute on. Just running through some of these quickly, we have at the top here this thinner silicon absorber. So we're looking at a concept now, and to go back to the point Dean made earlier, principally thin film technologies should be cheaper than crystalline technologies. We're using less material. We're using significantly less silicon. It's less than 1% of what you would see in a traditional crystalline solar cell. And what we're doing, we're actually implementing this already in production, is moving to much thinner cell designs. This means that we use less material. This means that our processing times are quicker, which means our productivity of the line is much higher, and it also gives us an increased performance in terms of the module power. We have other items as well, looking at the technology in the laser scribing and moving to thinner dead bands, so thinner scribing lines, which enables, again, higher module power. Unique front contact solutions for the transparent conductive front oxide, also giving lower material costs, so we don't have to rely on pre-coated glass. That enables us to have cheaper costs. Thinning the back end of line as well. This ties into what I mentioned before about material cost. efficiencies that can be achieved in the back end of the line when we're bringing in additional glasses, a lot of the material components. This really helps to bring down the cost. And looking at thinner modules, so reducing the overall weight, that obviously reduces material cost, but it also enables a broader range of applications to be addressed. And finally, I just wanted to put a slide up to summarize why thin film silicon, in particular, this is, again, our area of expertise, really has the potential to succeed. It should succeed, and these are the key points why. It has the lowest manufacturing cost potential. We firmly believe this. We live and die with thin film silicon. We're not looking at other technologies. This $70 per watt peak we have been publicly presenting for a long period of time because we have a huge degree of confidence in this. It's achievable with a single manufacturing line. I think this is very important. When we compare manufacturing costs with the large Chinese manufacturers, you have to bear in mind that they have multiple factories. They're vertically integrated. They have 500, 600, 800 to a gigawatt scale, and we're able to achieve lower manufacturing costs within a single factory. We readily available materials. We don't have any supply issues here. It does have a lower efficiency. Obviously, this is a disadvantage, which means that it's more suitable for certain applications than others. But when we start talking about utility scale, it means that we should be able to achieve the overall lowest cost of electricity, even though we have slightly higher balance of systems cost. And part of that ties into the yield performance as well. So jumping to some of the bottom points here, it's been seen, and we'll see more of this as the industry matures and we get more data from thin film installations, that thin film silicon, and the other thin film technologies do have a higher yield. So they're generating more kilowatt hours per installed watt peak than their crystalline counterparts. The other point here, just to mention again what Dean positioned earlier about the scalability. So this is, in the case of thin film silicon, this is a silicon technology. The core of this technology comes from semiconductors and flat panel displays, very mature, very successful industries that have been rolled out in significant scale over the last 20, 30, 40 years. And we've already demonstrated to date that this technology can be deployed quite quickly, it can be ramped quickly, and it can achieve some of the highest yields in the industry. So factories today are already running at 95% or higher with their yields. Okay, that was my...
Okay, thank you.